All right, so in Chapter 1, we're going to be talking about functions. And this first chapter is going to feel very familiar, or at least feel very similar to the first chapter from Algebra 3-4. We're going to do a lot of the same kind of topics. We'll provide some additional depth and look at things maybe in slightly different ways, but a lot of the content should feel recognizable and familiar. Maya? Of course. So let's start with our definition for a function. That was fast. Yes. I'm going to be right there. Okay, so a function is from a set D to R, where D is the domain and R is the range. That's an assignment such that, so this little ST is a common mathematics abbreviation for the phrase such that every element in the domain is paired with exactly one element in the range. And hopefully that feels like the familiar function definition that you basically remembered. Bless you. You're welcome. We're on high alert for manners this year. So there's a few different ways that we can represent a function. So does anybody remember any of these different ways that we represented a function? What was that? Okay, so like with an equation, is what you're saying, like f of x equals x squared or something? Yep, good. What else do we have? There's like 5 of these, I think. Common ones anyways. A graph, very good. Well, you should have spoke up. She took the credit for it. That's what you get for being quiet. Ben. Okay, set of ordered pairs. Good. Anybody else think of any? Similar to a set of ordered pairs. Sometimes we display our function just as an XY table. And then the last one is the one that none of the classes have remembered. So far, it was the mapping diagram. So we'll take a few minutes and go back and look at some of these and talk about how we know, or how we can tell if that represents a function or not. Let's start with the mapping diagram. So usually for a mapping diagram, we're going to draw 2 ovals to represent the sets for domain and range. Typically, the oval on the left is the domain and the oval on the right is the range. We then write in the names of some elements inside of those sets and usually put a dot next to it to represent where that element is in that set. I'm going to call the elements in my domain x1, x2, and x3. And similarly for the range, I'm going to call the elements y1, y2, and y3. And for the mapping diagram, we just draw an arrow to show the assignment of x's to y's. So in this case, is this mapping diagram representing a function? Yes, right? All of the x's are used, and they're all used just one time, which is basically what we're looking for. Everybody agree with that? So that's a function. What if instead the assignment looked like this? Is this a function? It is not. So if somebody that said no, why is this a problem? Good, not all the x's have been used, right? So we haven't used everything from the domain. So that's not a function. Okay. What if we had, say, this mapping diagram? Is this a function? Yes. So again, all of the x's are used, and the x's are used just one time. Does it matter that some y's aren't used? No. Does it matter that some y's are used more than once? No. All we care about is the x's. Okay. And then one last one. How about this one? No. What's the problem? Yeah, x1 is paired with two different y's. It's used twice, right? Very good. Everybody feel okay about the idea of what we mean by a function and kind of how to check in this context? Okay. The next situation I want to deal with is if we have an equation. So let's say we have something like x squared plus 2. Is this a function? Yes. How did you know? Great. So you guys have said that the graph of this function, or the graph of this equation, is a parabola, which I know is a function because it would pass a vertical line test. That's a perfectly reasonable assumption. You may have looked at this and gone, oh, that's just a quadratic function. I can recognize the form of this equation and know that it's a function. We studied it last year in Algebra 3-4. So this is a function. In general, if you have something where you just have a y to the first, and there's nothing else operation-wise going on with your y, it's probably going to be a function. An example of something that, or another example might be something like this. X squared plus y squared equals 4. Is this a function? No. Why not? Because it's the graph of a circle, which fails a vertical line test. So, that's good. Hopefully you remembered-ish from geometry or a previous math course. The equation for a circle is of the form x squared plus y squared equals r squared. And clearly a circle is going to fail a vertical line test. But the way I'm thinking about this is just there's something going on with the y's, right? We have a y squared instead of just a regular y. More often than not, if you see the y's been messed around with, that's probably a good indication that you should think very carefully about it because it might not be a function. If you just have like a y to the first, you're probably in a safe spot with that. More often than not, it would be a very tricky example to come up with something that failed to be a function if the y was isolated like that. You'd need a plus or minus or something in there to kind of make that work. Is everybody okay with that idea? Okay. In general, for an equation, if all else fails, the easiest way, and you're not sure whether it's a function or not, what should you do? Yeah, put in your calculator, look at the graph. Is an easy default way. So speaking of looking at the graph, you guys already mentioned that to determine whether a graph represents a function or not, we can use a vertical line test. Does everybody remember what the vertical line test is? Yeah? Okay. I'll just draw a couple of pictures here. So, if I look at the first graph, is this a function? Yeah, right? No matter where we draw our vertical line, we're only going to intersect the graph at least, or at most one time, right? How about the next one? Is that a function? Yes. What if I included like that extra point there? Is that a function now? No, right? Because I could draw the vertical line that intersects this twice. And the last one, is this a function? No, right? Again, I can draw a vertical line that intersects the graph multiple times. In this case, 3 times. Does everybody feel okay on that? All right. Again, hopefully that's pretty familiar sounding. We spent a good amount of time at the beginning of Algebra 3-4 talking about identifying whether something is a function or not. So I'm hoping that you still have a lot of that. Next thing I want to talk about a little bit is function notation. So when we say function notation, we really are talking about writing f of x equals rather than y equals. And to just kind of explain where that f of x notation comes from. So here's my domain and here's my range. So I have an x and I apply some transformation on that x. I'll call the name of that transformation, I'll give as f. This resulting value over here, I could think of as f of x. It's where x goes after I apply the transformation of f to it. But since it's also in the range, I could also call it a y value. So that's kind of where the notation for f of x comes from and why we're using it interchangeably with y equals and f of x equals. Is everybody okay with that idea? Again, nothing very technical there. It's just kind of giving you a background of why we can use these symbols interchangeably and where that symbol kind of comes from. When we write something like y equals 4x minus 3 or something, we have a name that we give to the x and y variables. We say that the x variable is the independent variable, and we say that the y is the dependent variable. The reason we say that is because we have the freedom to choose whatever value we'd like for x. It's independent. We don't have any restriction on that. The value of y, though, to determine that, we have to have the value for x. So my value for y depends on the value that I've chosen for x. So if I suppose I choose x to be 2, my value for y in that case would then be 5, right? Everybody agree? Okay. You guys' reluctance to answer that question made me nervous there for a moment, but I think everybody's okay with that idea. The next section in Chapter 1, we're going to talk about domains and ranges. And in this class, to describe our domains and ranges, we're going to use interval notation. So an interval notation is just a way to describe a continuous set or a certain kinds of infinite sets. So suppose I have the set of numbers that are less than or equal to 2. To write this in interval notation, I need to include a lower bound on this set and then an upper bound on this set. If I'm talking about x less than or equal to 2, the lower bound is negative infinity, right? The upper bound on this set would be 2. Now to finish my interval notation, I need to indicate whether or not those lower and upper bounds are included or not included in the set. So let's first consider the negative infinity. Is negative infinity a value that like x can have? No. Good. So to indicate that it's not included, we're going to use a parenthesis. If I look at the set x is less than or equal to 2, is 2 included in that set? Yes, because it's an or equal to inequality, so I'll use a bracket. So the parenthesis is for not included, and the bracket is for included. And when we write these intervals, we always go upper bound, comma, lower bound. Or lower bound, comma, upper bound. So it always goes small to big. Sometimes I'll see students write it in the opposite direction. Please don't do that. You're describing an empty set, most likely in that case. Because there would be no numbers from 2 to negative infinity. All right. Let's do a couple more examples of this. Not that I don't think you guys have this, but we do want to make sure. For this first one, I'm sorry, I want to go back and say one more thing. Notice that this set is talking about x's. So I would want to include one more piece with this interval and just indicate what variables we mean. So this little E symbol here just means is a member of. So on this one, -5 is less than or equal to y is less than 10. Since we're talking about y's, we would start that y is a member of. And then what's the lower bound for this set? -5. And the upper bound is 10. The -5 is included or not included? Included because of the less than or equal to, so that'll get a bracket. And the 10 included or not included? Not included because it's a strictly less than inequality, so that will get a parenthesis. Everybody happy with that? Okay. We'll do one more, and then we'll move on to talk about ranges. So here we have an OR inequality. Does anyone remember how we deal with the OR inequality, or what symbol we use to deal with that OR from last year? Okay, that's okay. So the symbol we use is the union symbol. So it's like the U with no tail on it. So that's going to be the same thing as my OR. In the language of sets, union is the same thing as the word OR. And then I'll just treat these two inequalities as their own separate intervals. So if I consider A is less than 2, what's the lower bound on that set? -infinity, and the upper bound is 2. And are those included or not included? They're both not included. The -infinity is not included because the infinities are never included. And the 2 is not included because the inequality is a strictly less than inequality. Now let's worry about the A greater than or equal to 5. What's the lower bound on that set? 5. And the upper bound is? Positive infinity. I write positive infinity. You don't need to do that if you just write infinity instead of positive infinity. That's okay. The negative infinities need a negative on them. I always just put the positive because it helps me differentiate a little bit easier, but you don't need to do that. 5, included or not included? Included because it's a greater than or equal to. The infinity, always not included for infinities. No, because this we're viewing all as one set. So you only need one of the A is a member of symbols at the very beginning. Good question. All right, so everybody feel comfortable with interval notation? I think primarily last year this was probably the notation used most commonly when describing domains and ranges. So hopefully this feels pretty familiar. I know in my class I used this as my default. I accepted other answers, but this was kind of the default one that I would write. Next thing we're going to talk about is domain. So let's look. Okay. That's okay. So let's look at a couple of examples here. Now, in regard to domain, there's kind of two different domains we can talk about. There's an implied domain and then a relevant domain. So an implied domain is just like the set of numbers that are algebraically possible to kind of plug into this. In this case, all real numbers are algebraically possible. There's no reason that I can't plug anything in there. Most of the time when we talk about domains, we're really talking about relevant domains. What the relevant domain is based, or is really just the numbers that are logically we can put in there based on the context of the problem. So in this course, really we're only talking about the real numbers. So in this problem, is the relevant domain still all real numbers? If I plug in any real number, am I guaranteed to get another real number back out of this? No, right? Why not? Because you could have a negative under the square root giving you an imaginary result. So we don't want to include anything that would give me a negative underneath that radical. Everybody agree with that? So the way that I'm going to think about that is I'm going to take the stuff that's underneath the radical, and I just need to make that sure that that's non-negative. So I just need to find the x's such that x minus 4 is greater than or equal to 0. Because anything else, I would be square rooting a negative, and that's not relevant to the context of this problem. So we'll just add 4 to both sides. And then if I want to write this as an interval, correct. So my domain is going to be 4 to positive infinity. Right? We're not including 1, 2, or 3 as possible inputs for x. Right? That's okay. But yeah, you're absolutely correct. Like you can't just pick the positive numbers. Right? You have to find the values of x where x minus 4 is non-negative. Is everybody okay with that idea? All right. What if we have this one? 3x over x plus 2. What's the relevant domain for this problem? Well, let me rephrase then. What could be a problem? What values of x could be a problem for this? Okay, so Kane says negative 2. Why is negative 2 a problem? Yeah, we're worried about this denominator being 0. So we want to find the values of x that make the denominator not equal to 0. So I can say that what I need is the x's that are not equal to 0, or not equal to negative 2. Everybody okay with that idea? Okay. How would I write x is not equal to negative 2 as an inequality? Because eventually we want to end this with an interval notation. How can I write x is not equal to negative 2 as an inequality? Well, hold on, what was that? Okay, but you mean negative 2, right? So we'll say x is less than negative 2, or x is greater than negative 2. Everybody, does that make sense to you guys? Feels about right. And then if I transform this into an interval, I have negative infinity to negative 2, union negative 2 to positive infinity. So it's everything except for negative 2. And this is maybe not obvious to think to do this, but after you've seen this trick, it's not also hard coming up with it the first time, a little trickier. Yes, sir. Oh, yeah, we should have. That's a good point. Thank you. I always forget this. I get going so fast, I'm so excited about the math. Does that happen to you guys? All the time. I thought maybe it would. So yeah, I forgot the X is a member of. Thank you. And our last example here is going to be V of S equals S cubed, where V of S is the volume of a, not a sphere, you dummy, that's a cube with side length S. What would the relevant domain be here? About the context of what we're talking about. What variable is the independent variable in this case? Is it S or V of S? It's S, so the domain's going to be relevant to S. And what is S representing here? A side length. So what can I say about those values? What do they have to be? Positive. Everybody okay with that idea? Now, I'm not positive on the text definition of a cube, whether that would include like something with zero side length that's basically just a single point. If we're counting that as a cube or not, that would be something that if you gave me S is greater than or equal to 0, I'd probably count that as well, as it's not really clear whether I'm including that single point as a cube or not, at least in this context without a very careful formal definition of what we mean by a cube. But definitely you can't have negative side length. We know that. A zero side length, whether we count that or not, is maybe not clear. But I think it's probably most natural to call this greater than 0. So if I turn that into an interval, we just have 0 to positive infinity. Everybody happy with these domains? Hopefully not too bad, right? Should feel pretty familiar, similar to things that we did last year. Last thing I want to talk about today are ranges. Ranges are almost always going to be much harder to determine than the domains. One of the easiest ways to determine the range would be to type the function into your calculator and look at the graph. You should be able to get a good idea of what the upper and lower bound are for the y coordinates by doing that. I want to focus instead today on determining ranges without having to rely on our calculator, although it's a perfectly reasonable thing to do. I'm going to go back to these 3 examples we just did and now worry about the ranges. I'm going to write that work in a different color. Say I'm going to do blues next to it just so nobody's confused at what I'm doing. Everybody good with that? So there's kind of lots of different ways that you can think about determining these ranges without looking at the graph. And I'm going to do a couple of different approaches here. So if I look at the first one, the f of x equals 2 times the square root of x minus 4. really the function going on here is this square root function, right? And if I look at that square root function, I'm going to try to determine, is this function always increasing or decreasing? If it's always doing one or the other, it's pretty easy to come up with the range just kind of using a little bit of common sense. I notice that the square root of 1 is 1, the square root of 2 is like 1.4, square root of 3 is like 1.7, square root of 4 is 2. So as those x's are increasing, the y is also increasing. Everybody kind of see that? So I know that this function is increasing throughout. Everybody feel comfortable with that notion, how I just kind of reasoned that out by looking at the behavior of my function and what I know about square root functions from last year? So I know then the lower bound for the x is going to correspond also to the lowest y coordinate on the graph. Everybody agree with that? How would I find that y coordinate? Well, I know what the lowest or the lower bound for the x's is. How can I figure out the lowest or lower bound for the y's? I have a rule here. What does this rule do? It turns x's into y's, right? You could find the inverse, and we'll do that later, but this is, I think, a little bit simpler. So all I'm going to do is I'm just going to plug 4 in for x, and that'll give me the y coordinate, right? Do you guys agree with that? So when I plug 4 in for x, I get 0. Can we all see that? And since 4 was included, obviously 0 is going to be included. When I plug infinity in for x, what do I get? Still infinity, right? Doesn't matter what you're doing to that infinity. Square root of infinity, still infinity. 2 times infinity, still infinity, right? So there's my range. If I look at this next one, can I do the same trick here? Is this always increasing or always decreasing? It's not, is it? So there's times where it's increasing and there's different times where it's decreasing. So that's a little bit of a problem for me. So what should I do instead if I don't have that? What I'm going to do instead is find the inverse. So I'm going to treat this like a proportion and cross multiply. Because to find an inverse, the first thing I want to do is get the x by itself. So I just did a cross multiply to get rid of the fraction. Everybody okay? I'm now going to distribute my y. I wrote it that order. Usually write them in alphabetical order in that situation. And then I'm going to move the x's all to one side. And then notice on the left-hand side, each of those terms contains an x. So I can take a greatest common factor of x from the left-hand side. And to get x by itself, I'll just divide by 3 minus y. And ordinarily, if I was finding the inverse at this point, I would swap the x's and y's. I'm not going to do that here because what I care about is, if we're talking about range, I care about the y coordinates. If I look at this, are there any values of y that are going to get me in trouble? 3, right? Because this is the denominator of a fraction, I need that y is not equal to 0. So I know that y cannot be 3. So then I can say y is a member of negative infinity to 3 union 3 to positive infinity. So, okay, we're going to interrupt me.
This interruption before we head to
So
community time.
many interruptions.
We just wanted to announce that after everyone is in community time in the high